This is John Black, Super Chemist. This video is part 6 of a playlist called Frames of Reference, and this individual video is called 20 Physics Laws and Experiments that Prove Earth is Accelerated Frame of Reference. First thing I want to bring up is that we're not including spinning or orbiting. Okay, obviously if it's spinning, the Earth is automatically an accelerated frame of reference, but we're going to take that out of the equation. Orbiting doesn't have anything to do with acceleration, but most people think it does, so we're going to take it out of the equation too. So our planet Earth is just sitting there. It's not spinning, it's not orbiting, it's just constant velocity going through space. It is still an accelerated frame of reference at that point. We're going to go over 20 reasons why. 1. All inertial frames have the same physics results. This is outer space where you're floating, the ball floats. I can name a billion experiments that don't line up with outer space that lines up on Earth. Earth has totally different physics results. Number 2, floating ball experiment. That's where you take a ball and you hold it out and you let go of the ball without putting any force or anything on the ball. See what the ball does. If the ball floats relative to you and doesn't move relative to you, then you are floating. You are in an inertial frame. But if the ball accelerates anywhere, then you are in an accelerated frame of reference, and we all know what happens when you have a ball. It does on Earth. It does not float. It accelerates down to the ground because you are in an accelerated frame of reference. What about the accelerometer experiment? When you have an accelerometer and you drop it on Earth, the accelerometer, while it's falling, says it's in free fall. There is no acceleration. If you take an accelerometer and you put it on the surface of Earth, the accelerometer will tell you you are accelerating at 9.8 meters per second squared. Reason 4, 100% of the things on Earth accelerate to the ground. If they all accelerate to the ground, then you're in an accelerated frame of reference. Number 5, 2 infinities plus 1 infinity. What does that mean? You can think of an infinitive number of rockets, all different sizes and shapes, all of them moving at 9.8 meters per second squared acceleration. Same thing with this rotating thing. You can imagine infinitive number of rotating things that are different sizes, different this, different that, but if they all have the same 9.8 meter per second squared, like on Earth with the acceleration, you have 2 infinities where the physics results line up. They're the same as you get on Earth. And these are both accelerated frames of reference. Here's an inertial frame of reference. You're out in outer space. You're just floating. None of the physics. You can think of an infinitive places in outer space where you're floating. So you have an infinitive number of inertial frames where the physics results are not the same as on Earth. But you have 2 infinities of accelerating frames that do line up with the same physics results on Earth. Number 6, time dilation equations. You can see from the time dilation equations, Earth is an accelerated frame of reference. You can't have time dilation without acceleration. Does the acceleration cause the time dilation? No, the velocity does. But you can't change your velocity from 0 to 1 or 1 to 2 unless you do some acceleration. These do not work out if an Earth is inertial. When we have the rocket time dilation equations, we say that the top is always the bigger number because it's the time dilated time. So that would be the rocket. This here would be the rotating thing. And the bottom would be the inertial state. And they keep saying that it's Earth. Earth is not inertial. Okay, this is space. M stands for gravity machine. S stands for outer space. So this all makes sense. But when you get to Earth, they say that Earth is inertial here and here. But then down here, they're like, nope, it's time dilated. It's got acceleration. Here we go. We'll put Earth up here and outer space out here. See, they don't mesh up. My way, they all mesh up. This top one is touching a gravity machine. This one is touching a gravity machine. This one is touching a gravity machine because they are all accelerated frames of reference. And then the bottom one is outer space, just floating inertial. How could this be if Earth is inertial? Why is it here where it says time moving. It's time how are you getting time dilation on Earth if there's no acceleration? That's what I want to know. How is Earth inertial in the first two time dilation equations for the rocket and for the rotating thing? And then in the third equation, where you're talking about time dilation on Earth, now all of a sudden Earth is not inertial, outer space is inertial. This doesn't, what? You can't be both. Pick a lane, man. Pick a lane. 7. All inertial frames have zero acceleration. Come on, man. Earth has acceleration all over the place. 8. Law of inertia.
This is just the law of inertia. An object moves with a constant velocity unless an unbalanced force acts on it.
Things don't move at a constant velocity on Earth. They move like this. They're not in a straight line. They're not in a constant velocity. Gravity, and you can say, well, there's a force on. No, gravity is not a force that forces baryonic matter. It only forces space-time. It doesn't do anything to the baryonic matter or regular matter. All it does is it changes the space so that the path that the ball goes in, it goes in a different way, different path. Doesn't do anything. Gravity don't do anything to the ball. That's not a force on a ball. Number 9, the geodesic math law. This not only is a math law but a physics law. If you have, and it states, if you have two geodesic straight line paths, right, on curved space, and you have two men. See these two men? They're walking at constant velocity along their straight line geodesic path. They will accelerate towards one another. That's a geodesic math law. Okay, they will accelerate towards one another. You can see the geodesics up here. I drew the line so you can see the acceleration. If I split this up into units of time, 3 units of time, you can see here it's a little line, here's a bigger line, here's a giant line. It is obviously acceleration. The North and the South Pole are accelerating. Graph law. Curved lines on a graph indicate acceleration. Equivalence principle. Anything that has gravity is equivalent to anything that is accelerating, like a spaceship. Number 12, acceleration is any deviation from a straight line path. This is supposed to be our straight line path, yet you can see the North and South poles are deviating from their straight line path. That's the definition of acceleration. Earth is an accelerated frame of reference. Constantly changing your direction like this, that is a form. You can see the planet North and South is going this way. It is deviating from its straight line path. It's inertial straight line path. It's constant speed path, and it's constantly accelerating in another direction. This is literally the definition of acceleration. That means North and South, if they're in an accelerated frame of reference, so is all of Earth. 13. It's a law, physics law. In order to stand still relative to the universe, when I say the universe, I'm just basically saying Earth, and how the universe would perceive you relative to the Earth. In order to stand still in curved space-time, you are required to accelerate, just like over here. Here's flat space-time. You don't have to accelerate to stand still. You just stand still. And what about this guy? He's on curved space. What's going to happen to this guy? He has wheels. He's going to roll down a hill. You're required, when you're in curved space, you're required to accelerate like this guy has a little rocket on it. Now, he can stand still relative to the rest of the universe and the rest of the planet by keeping that acceleration the same as the acceleration downward, meaning gravity. And he can stand. That's the only way he can stand still in curved space. So look up here. You have this rocket. If he didn't have his rockets on, he would just fall straight down to the Earth. The only way he can stand still, meaning, let's say he's 100 miles away from the Earth. The only way he can stay 100 miles away from the Earth is have his rockets on. Otherwise, he will fall down to the planet. If you don't have your rockets on, there is another way that you can stop from rolling down the geodesic, and that is to put some ground there, just like over here. You put ground, or you can have a rocket. Either one, you're going to now stand still relative to the rest of the planet. So just like over here, you're going to stand relative to the rest of the planet, you're going to be standing still. Same way with this rocket ship. How can these two be standing still relative to each other, and one is accelerating and one is not? He is required to accelerate in curved space-time to stay standing still relative to the rest of the universe. Same way with this man here. No, he's not accelerating, but the space-time is accelerating through him. And he either got to fall and go along with that space-time, or he's going to get stuck here on the planet. He's going to be stopped. So relative to space-time, this man is accelerating. He is required to be accelerating. Otherwise, how can he be standing still to the rest of the universe and the rest of the planet? Same over here. How does he stand still? He puts his rocket on. How does he stand still? He puts a ground here, and the ground prevents him. Think about it. This guy in the spaceship right here, he's accelerating so that he can stand still relative to the Earth. This man is, you say he's not accelerating, but all the physics that this guy in the spaceship gets, is this guy is going to get the same exact physics. They get the same exact physics. And they're both standing still relative to each other. That means, and this guy out here, he's floating in space. His ball is floating. This guy has his ball on the ground. This guy has his ball on the ground. So you're telling me that this is inertial? Like this guy here floating. Even though this guy is accelerating, we know he has his rockets on. And all his physics line up with this guy. Obviously, Earth is an accelerated frame of reference. I hope you can see by now, you only have two main frames. You're accelerating or you're not. When you accelerate, you always 100% of the time create gravity. So if you have gravity, you're an accelerated frame. If you don't have gravity, you ain't in an accelerated frame. It's not complicated. These are the things they tell us. I'm not saying, I'm not bringing these are their laws. They're the ones who have the equations saying that you can, in order to stand still in curved space, you're required to accelerate. You have to be in an accelerated frame of reference in order to stand still. That's their law, not mine. Number 14, the spinning ball on a string experiment. When you are in an inertial frame, you can spin a ball on a string and you will make a two-dimensional circle here. But on Earth, this does not happen. We make a conical pendulum when we spin around a ball on a string. This indicates that we are in an accelerated frame. Otherwise, we would have a two-dimensional non-conical, not conical shape when we were done spinning our ball on a string. 15, F equals ma. If you have a ball and you give it some acceleration, once you stop the acceleration, the ball has to move in constant velocity in a straight line if you are in an inertial frame of reference. On Earth, we do not have that. We get a parabola type shape. Now the rest of these are basically common sense more than laws. But number 15, there's a ground on Earth. Nothing floats. It's not the simplest physics. It's not the simplest of math. There is an up and down relative to a ground. In an accelerated frame, things accelerate. Everything accelerates on Earth, or it's stuck to a ground. And the last thing, number 20, these people, they keep saying, on Earth, relative to me, nothing is accelerating in my frame. First of all, if you drop anything, it accelerates in your frame. Secondly, you can say the same thing on this ship that has its rockets on. I forgot to draw the fire. But if this guy is accelerating, yeah, relative to him, nothing is accelerating in his frame either. That ball is just stuck to the ground, just like this ball is stuck to the ground. That doesn't mean that you're not in an accelerated frame, just because nothing accelerates in your frame. And secondly, everything accelerates in your frame. In both of these, the rocket and the thing. If you let go of anything, it's doing one of two things. It's either accelerating to a ground or it's stuck to a ground already. That's how you know you're in an accelerated frame of reference. When you're in an inertial frame, nothing is stuck to anything because there is no ground. There is no up and down. There is no acceleration. There is no gravity. All acceleration creates gravity. So if you have gravity, automatically you know you're in an accelerated frame of reference, because there's no other way to get gravity other than through acceleration.